Have you ever noticed? No matter how deeply we study the universe, there is one theory that consistently dominates our understanding of its origin: the Big Bang Theory. But is it possible that the Big Bang Theory is only a fragment of the universe's origin story? What if, behind the universe we live in, there is a mirror image counterpart, a companion universe where time flows backward? Imagine, the universe is not a single event, but is composed of two universes that are mirror images of each other. In the same instant, these two universes were born together, but their directions of time are completely opposite. As time flows forward in our universe, is another universe also flowing backward, carrying a reverse impression of the world we know? This hypothesis challenges the traditional cosmic model, but its simplicity might provide us with answers to questions that have puzzled scientists for years. For instance, why is the universe so uniform on a macroscopic scale? Why does time always seem to flow in one direction? Perhaps the existence of this mirror image could also be the key to finally solving the mystery of dark matter. Imagine, the starting point of the universe wasn't just the Big Bang, it was actually a boundary, a threshold separating two symmetrical universes. In the universe we inhabit, particles follow the physical laws we are familiar with, governing everything. But in the other universe, all the laws of physics are reversed. This seemingly sci-fi hypothesis is not without foundation. Its roots lie in a key principle of physics, CPT symmetry. According to this principle, particles exhibit symmetry under the mirroring of charge, C, parity, P, spatial inversion, and time T. Symmetry means that every particle has its mirror version. If this theory holds, it might provide us with the answer to the mystery of dark matter. To verify this hypothesis, scientists have studied gravitational patterns in the Milky Way and the subtle differences in the cosmic microwave background radiation. In fact, the origin of all this can be traced back to the early 1980s. At that time, scientists proposed a brand new theory in an attempt to answer two core problems that had long puzzled them in cosmology: the horizon problem and the flatness problem. First, imagine that the universe is not an endless void, but more like an expanding balloon. This balloon was very small in the early universe, not nearly as vast as it is today. But in its expansion process, it maintained a surprising uniformity. This assumption raises a question: why do regions of the universe separated by billions of light-years appear so similar? This is the crux of the horizon problem. When we observe particles at opposite ends of the universe, their temperature and structure are almost identical. But according to the laws of physics, they could not have interacted or exchanged information in any way. To solve this dilemma, in 1981, scientists proposed the theory of inflation. This theory holds that, in an extremely short period after the Big Bang, the universe underwent an exponential expansion phase. The speed of the universe's expansion was so fast that regions that were once in contact were instantly pulled apart, eventually forming the uniform universe we see today. Thus, the inflation theory not only explained the horizon problem, but also provided an answer for the flatness of the universe. Next, we need to focus on how inflation solves the flatness problem of the universe. According to Einstein's general relativity, the geometry of the universe is closely related to its matter density. If the density of the universe is exactly at a certain critical value, then its spatial structure will exhibit the flat shape we are familiar with. And the inflation theory, by stretching space-time itself, eliminated any curvature from the initial state, making the universe appear almost perfectly flat on a large scale. Even more surprisingly, during the process of inflation, the tiny quantum fluctuations in the universe, those almost imperceptible waves at the subatomic scale, were rapidly stretched to a cosmic scale. These tiny variations spread throughout the entire universe and, over time, gradually evolved into the galaxies, stars, and other celestial bodies we see today. In other words, these almost imperceptible disturbances actually became the foundation of all the structures in the universe. After the expansion of the universe ended, these initial density differences began to leave a deep imprint on the cosmos. Regions with higher density attracted more matter through gravity, gradually forming a sharp contrast with regions of lower density. Over time, these high-density regions eventually evolved into the structures we see today: galaxies, stars, and galaxy clusters. This evolutionary process has left valuable clues in the cosmic microwave background. About 380,000 years after the Big Bang, the CMB first appeared, becoming the earliest light we can observe. It is a snapshot of the universe in its youth, recording the state of the universe at that time. During that period, photons and matter were tightly coupled, forming a hot, dense plasma. But as the universe expanded and cooled, photons decoupled from matter and began to travel freely through space. The temperature fluctuation patterns carried by these photons became a permanent imprint, revealing the distribution of matter in the universe at that critical moment. Through this cosmic snapshot, we can see that some photons appear slightly cooler, while others are slightly warmer. These differences are directly related to the density of different regions in the universe. When photons leave a region of higher density, they need to expend more energy. This causes these photons to be cooler when they reach an observer than photons from a low-density region. This phenomenon is known as gravitational redshift and is the fundamental reason for the temperature fluctuations in the CMB. These temperature variations not only reveal the density differences in the early universe, but also outline the structure of the universe at that time. The European Space Agency's Planck satellite, launched in 2009, further deepened our understanding of this process. The Planck satellite measured the CMB with unprecedented precision, revealing the detailed structure of these early seeds. Through the analysis of this data, scientists confirmed that the patterns in the CMB are highly consistent with the predictions of the inflation theory. This result provided strong support for the validity of the inflation model and has made inflation an important cornerstone of modern cosmology. However, although the inflation theory provides a convincing framework for explaining the rapid expansion of the universe, there are still some major unsolved problems. One of them is the fine-tuning problem. In order for inflation to work in the way we observe, certain initial conditions must be set with extreme precision, almost like calibrating a highly complex machine. Even the slightest deviation would prevent it from operating as expected. This makes one wonder, why was the universe so perfectly tuned at its birth? These initial conditions are crucial for the inflation process. Even a tiny deviation could lead to the interruption of the inflation process, thus preventing the universe from reaching the flat, smooth state we see today. In response to this, some theorists have questioned whether there is a deeper reason to explain this fine-tuning phenomenon, or if the inflation theory is only a partial answer, and if there are alternative theories that require fewer initial conditions. Another major challenge facing the inflation theory is how to reconcile it with particle physics. In theory, if we could understand fundamental particles more deeply, we might be able to reveal the mechanism behind inflation. Supersymmetry, SUSY, is an important concept in particle physics that goes beyond the framework of the standard model. Supersymmetry hypothesizes that every known particle has a corresponding superpartner, a heavier version. If this theory holds, it could explain the structure of the universe and even provide clues to solving the dark matter problem, while also providing support for the high-energy conditions required for inflation. In this regard, the ATLAS collaboration at CERN is at the forefront of research. By using the Large Hadron Collider LHC, the ATLAS team is searching for various superpartner particles, especially charged and neutral particles. They are very crucial because they might be the key to finally solving the mystery of dark matter. Dark matter, although it constitutes the majority of the mass of the universe, has always been impossible to observe directly. However, despite using more advanced methods and higher energy collisions, we have so far found no direct evidence of these particles. However, for now, supersymmetry remains a potential but unproven theory. Its profound impact on cosmology is still to be verified. For centuries, physicists have been searching for a unified theory that can explain all particles and forces. This is the so-called theory of everything. The starting point of this quest can be traced back to Einstein's later years, when he devoted himself to combining gravity with the other known forces. Decades later, Hawking took up the baton of this quest, proposing that the answer might be hidden in a revolutionary new concept, M-theory. M-theory is one of the most ambitious ideas in theoretical physics. It proposes that the universe is not composed of the point particles of traditional physics, but of extremely tiny, vibrating strings. More importantly, these strings are not just mathematical abstractions. The vibration of each string corresponds to a fundamental particle. One type of vibration might manifest as an electron, while another might produce a photon. One of the core appeals of M-theory is its ability to describe gravity in a mathematically consistent way. This is significantly different from earlier models, which often led to meaningless infinities when dealing with gravity at the quantum scale. M-theory includes gravity through specific string vibrations, thus introducing a hypothetical particle, the graviton. Unlike the particles in the standard model of particle physics, the graviton in M-theory follows quantum rules and does not break down at the microscale. However, M-theory requires us to completely expand our understanding of space. The three-dimensional space we are accustomed to is replaced by a universe containing 11 dimensions, 10 spatial dimensions, and 1 time dimension. According to this theory, some of these dimensions may be compactified, extremely small and curled up, so that they are completely invisible at everyday scales. These hidden dimensions might influence the fundamental properties of particles, explaining why the laws of physics appear in the form we observe. So, what does all of this have to do with a mirror universe? M-theory provides a framework that suggests the existence of multiple dimensions, and even multiple universes, is not only possible but expected. This is particularly striking when considering a mirror universe. According to M-theory, the universe may not exist in isolation, but as a brane in a higher dimensional space, parallel to other branes or universes. In this model, universes may exist in pairs, symmetrically opposed in a higher dimensional space. A mirror universe might be a parallel brane with a reverse configuration, where fundamental aspects like time might flow backward. Since M-theory allows for higher dimensions, it provides a possibility for interactions between these universes. They might even influence observable physical laws or phenomena, such as the distribution of matter or the flow of time, through subtle interactions. By introducing extra dimensions and principles of symmetry, M-theory provides a theoretical basis for the natural emergence of a mirror universe. This concept is closely related to the mirror universe hypothesis because it suggests that a mirror universe might follow the fundamental symmetries and higher dimensional structures proposed by M-theory. In particular, the symmetry between particles and antiparticles might be reflected on a cosmic scale, making one universe the time-reversed mirror image of the other. For Hawking, M-theory's ability to explain multiple universes, including the potential existence of a mirror universe, was precisely its appeal as a complete model of reality. It provided a theoretical basis for the existence of a mirror universe and a viable framework for exploring how these universes might interact with our own. So what exactly is a mirror universe? The mirror universe hypothesis proposes a radical alternative, challenging the traditional inflation model. Its core idea is this. Imagine that our universe did not undergo a violent expansion after the Big Bang, but that two universes were born simultaneously, one moving forward in time, the other flowing backward in time. In this model, the corresponding universe's time flows backward relative to ours, thus creating the mirror image of our universe's history. This idea is based on a fundamental principle in physics, CPT symmetry. CPT symmetry means that for every particle in every process, there is a dual with reverse charge, C, parity P, and time T, constituting the mirror image of our universe. If this hypothesis holds, the mirror universe would be composed of antimatter, not ordinary matter, and would unfold in reverse time, creating a balance with our universe's forward motion. Antimatter is key to this concept. Take an electron or a proton, for example. These matter particles each have an antiparticle with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other and release energy. According to physicists' speculations, matter and antimatter should have been formed in almost equal amounts at the Big Bang. However, today's universe is almost entirely made of matter. The mirror universe hypothesis may provide an explanation for this mystery. If a mirror universe composed of antimatter was formed at the same time as our universe, then the asymmetry we observe between our universe and the mirror universe might simply be because our universe has unique properties relative to its mirror image. The concept of a mirror universe also provides a new perspective for solving the fine-tuning problem proposed by the standard inflation model. The conditions of the Big Bang, such as density, temperature, and expansion rate, must be precisely tuned to produce a universe like ours. If our universe is paired with a mirror universe, then this symmetry might naturally create stable conditions, thus not requiring such fine-tuning. If we view the Big Bang as a mirror between two universes, then we get an alternative model that both conforms to the known laws of physics and provides an explanation for the mysteries in existing cosmology, expanding our imagination beyond the observable universe.